So section 4 talks about something called optimization. This is really applications of everything that we learned in section 3, finding mins and maxes using the first and second derivative tests. You actually probably did a lot of these in pre-calculus. You just used your graphing calculator to find those maxes or mins. So for this, you actually need to use calculus to find your answers. But you don't necessarily need to justify everything that you're doing like you did in section 3. As you get started, I just have 3 hints here. I'm sure we'll talk about more as we go through some of these examples, but a lot of these, drawing a picture can help you a lot. Thinking through some geometry rules that you might have, some area formulas or volume formulas could be helpful. And also just thinking through a concrete example. By that I mean a specific example, a specific situation rather than something that is using variables, and that might get you started along the right track. So our first example says determine the maximum area of a rectangle that can be enclosed with 200 meters of fence. Let's start out with a picture. Okay, we have a rectangular area. And I want to maximize the area. So for area, we'd say that we have maybe x, we have y there, and so area here would equal x times y. And that's a really good place to start. Figure out what you want to maximize. Sometimes that can be really easy. Sometimes you might have to work out a little bit longer. But what I want you to notice is that right now we have 3 variables. We've never taken the derivative of something with 3 variables. It's always been 2. And so a lot of times your job will be to eliminate one of those variables. We want to differentiate because, remember, the first derivative test or second derivative test, we use those ideas in derivatives to find the maxes or mins. So how do we eliminate one of those parameters? A lot of times we look at the other info that they're giving to us. So the fact that there's 200 meters of fence. So keep in mind that this is also a length of y and this is also a length of x. And if we use the idea of perimeter, I get 2x plus 2y is going to equal 200. And I could go and kind of solve for one of these variables. I might solve for y, so eventually if I move things around I would get y equals 200 minus 2x all over 2, which eventually will just get you to y equals 100 minus x. And so this is going to be kind of an important piece to the puzzle. And a lot of times when you do that, a little separate thing there to help us out. So back up to the thing that we want to maximize. I want to maximize area, and now I know that area is going to equal x times 100 minus x. Hey, we got 2 variables, a and x. And so one other thing that I might do here is just rewrite this one more time, 100x minus x squared. Okay, now let's think about that first derivative test. That first derivative test says that a max or a min only occurs when the first derivative equals 0. So I'm going to take the derivative of area, take the derivative with respect to x, and from that I would get the derivative on the other side, right? This is just like y prime or a prime. Over here I'd have 100 minus 2x, and our job is to figure out where that would equal 0. So where does this thing equal 0? So I go ahead and I could actually go ahead and solve this out a little bit. I think you guys can probably see that x would have to equal 50 for this to work out. So if x equals 50, and we go back somewhere, maybe this would be a good place to help us figure out what y is. If I put a 50 in for x, that means that y has to equal 50. Hey, we get a square. What do you know? The maximum area occurs in a square. There's got to be a rule for that somewhere. And so we want to know the maximum area, so area for this shape would be x times y, or 50 times 50, which is 2,500. And units for this, that would be meters squared. So if you notice, there's my answer. That's the maximum area. I'm using calculus ideas. I haven't really proven that it's a max. We can kind of, if there's only one point where this would work, we can kind of assume that it's going to be there. Technically, I should probably do a little bit more testing on some free response questions. We will, but just to get us started, that's kind of what we would be thinking about there. I guess before I switch, another thing to think about, I know what the shape of this probably looks like. It's an upside down parabola, so if I found any points like that, it's got to be a maximum. If they say justify, we'll talk about how we can justify that. Okay, next one, we have a rectangular box, has a height of h, a square base with sides of x, has an open topped box, and it has a volume of 32 cubic centimeters. We want to come up with something for surface area and then find that minimum surface area. Okay, so the first thing we might do here is draw some sort of a picture of this. I do not claim to be an artist, but there is my box. It's a gross box, but I want you to notice that I do have my dotted lines in there, so I'm pretty proud of that. We are trying to minimize the surface area, so let's start off by finding a formula for surface area. Surface area for this, we have a base that is x squared, and then we have 4 sides, and all of them have the same dimension. They're all x by h. So we're going to have plus 4 of these, 4x times h's. And that's how we come up with surface area. Now, we technically have 3 variables here. Surface area is kind of one variable, one idea. We have x's and we have an h. So again, we want to eliminate one of those before we can actually take a derivative. They tell us some things about volume, though. So let's come up with a volume formula for this. Volume for this particular shape would be x squared times h, right? You multiply width times length times height. We know that the volume is 32. And if I think in this case I might solve for h. I know that h would be x squared. I'm sorry, I did that wrong. And of course, there we go. Technology can be a pain sometimes, but I think we got it right. Height would be 32 divided by x squared. So I can now take that, plug it in up here, and see what happens. I would get surface area equals x squared plus, now I know, well, I'll just write it all out for you guys. Okay, it's going to be 4x times 32 over x squared. That looks kind of gross. We're going to clean things up a little bit before we take a derivative because it will help us in the long run. So we'd say that surface area equals x squared. 4 times 32 is 128. And then I'm going to rewrite the x's like this. Hopefully that makes sense to you. It's going to be a little easier to take the derivative because now we're at the point where we're taking the derivative with respect to x. So remember, that's kind of like one variable there. Surface area is one idea. It's going to equal 2x minus 128 x to the negative 2 using the power rule there. And I want to know where this thing will equal 0. So where will 0 equals 2x, and then check this out, we're going to have a minus, we're going to write this as 128 over x squared. Where is that going to be true? One thing that might make this a little bit helpful is to combine these two ideas. So have them have a common denominator. If they have a common denominator, and this may not be the only way to solve it, but this is just kind of how my mind is thinking right now, I would get 2x cubed minus 128 all over x squared. See if that makes sense to you before we move on. Okay, I'm going to hopefully shrink everything here. Hey, there we go. Just so I have a little bit more room. And from there, I'm going to multiply both sides by x squared. That's kind of what I'm thinking, but really, if I want to know where this thing equals 0, I just need to know where the numerator equals 0. But I kind of think of it as multiplying both sides by x squared. I could then divide both sides by 2. So I would get 0 equals x cubed minus 64. And so really I'm wondering, where does 64 equal x cubed? Any ideas? Any ideas? That would happen when x equals 4. So again, because we only found one point where this is going to work, we could investigate a little bit more. But I do know at the very beginning that I'm dealing with x squared plus this stuff. That's going to have a minimum spot. We could look at a graph of this if that would be helpful, but more than likely this is going to be where a minimum occurs based on the question. We could prove things a little bit better. We can kind of take for granted, at least at this case, at this time, that this is a minimum. So x will equal 4. How do we figure out what h would be? We go back over to here and we figure this out a little bit. 32 divided by 16 would be 2. So that means that we have a box that is 4 by 4 by 2. Those are all in centimeters. And the minimum surface area, if we multiply that out, equals 48 centimeters squared. If we went through and we calculated everything out, we could plug it right back into the top, if that would be helpful as well. But that's where what our final answer would look like in the end.